Hello, welcome to this presentation. My name is Tayeb Lemlouma. I am an associate professor at Rennes University and the research member in the IEEE CNRS lab in Lannion City in France. In this talk, I will present our last research on algorithms for the Internet of Things. This work is published in the IEEE 25th Symposium on Computers and Communication ISCC in July 2020. In this work, I will focus on IoT applications with data and temporal accuracy requirements. The Internet of Things, IoT, is an expansion of Internet communication and interaction between human and applications through a new dimension of things. IoT is going to spread the digital revolution to our living environment with several objects surrounding us, or the equipment surrounding us are becoming Internet-enabled devices. The number of connected things is exponentially growing in the last years, with up to 25 billion devices expected to be part of the IoT ecosystem by this year. IoT has paved the way for applications in many horizontal and vertical markets, such as smart homes and transportation. For instance, in healthcare, the use of IoT is inevitable, thanks to the wide variety of used applications and the numerous enhancements in resources optimizations, cost saving, scalability, comfort, etc. IoT applications are still facing enormous challenges. As IoT devices play a major role in critical application and services, it's important to satisfy data and temporal accuracy requirements in applications. Another challenge is prolonging the lifetime of battery-enabled devices, in particular with energy-hungry transmission modules. In many applications, IoT devices regularly send and transmit data to a central node. This requires to identify a sampling and transfer strategy which is more efficient than the conventional periodic sampling method. One of the key questions is how to reduce the usage of IoT resources and extend the lifetime of devices. Proposed strategies for IoT devices should simplify the computing operations and memory usage and consider the hardware and the software limitations of things. Sampling, data and communication cooperations are the pillars of existing strategies. Context-aware and event-based sensing are relevant to reduce the transmissions between the sensor and the sync nodes. We use it in our previous work where we only consider the situations when a change in the surrounding context or the tracked data is detected. Major strategies consider the following conditions. First, send on delta, SOD. Here the difference between the last sensed value and the last sample sent is higher than a given threshold. Second, send on prediction, SOP. Here the expected value exceeds the previously sent value by at least a threshold. Two extensions of SOD are the send on energy and send on area strategies, where the considered difference between current and last values are the energy of the cumulative integral of differences. In this work, we aim to avoid the recourse to computing intensive models such as learning strategies with reinforcement learning, neural and recurrent neural networks, etc. For this, we adopt a less complex and energy-hungry ranging approach suitable for the limitation of IoT devices and networks. To the best of our knowledge, our proposed approach with the three proposed algorithms is the first dedicated to IoT devices that comprehensively complies with accuracy and energy requirements with a presented degree of efficiency and performances. The effectiveness of our proposal is demonstrated in terms of adaptability, accuracy, reduction of data transfer, and energy saving. The proposed algorithms are relevant for applications requiring long sensing periods and high sampling rate. Bollinger Bands is an analytic method developed by John Bollinger in the 1980s. It's used to compare volatility and relative prices in one analysis period. Bollinger Bands represent a technical indicator consisting of three lines or bands: lower, mid, and upper bands. The middle band is a simple moving average of a certain number of previous closing prices. Both lower and upper lines define the data volatility based on the standard deviation from the midline. Lower and upper bands are derived from a multiple of the standard deviation of a certain number of consecutive last closing prices plus or minus the mid-band. The difference between the upper and lower bands from the simple moving average is the same. The gap between the two lines widens if volatility increases, and in contrast, it narrows when decreases. In our context, the Bollinger Bands principle was used by Cuella et al. In 2016 as an efficient approach to reduce the sampling rate of IoT devices. To do so, Bollinger Bands are adapted with the called vertical distance dynamic estimation or DynVD. For unacquired samples, DynVD at time t is the mean of differences between the new values and estimated values using linear approximation.
DynVD at time t is the sum of differences between expected and real values at time t minus e. K is a factor that controls the width between the lower band and the upper bands of the time series. X hat is calculated using the two row values xt0 and xt0 minus n plus 1 sensed by the IoT device.
In DynVD, a new duration between two sensed and transmitted data, which means a new time slot, is defined with the new formula.
Delta max is a fixed maximum waiting period. Phi is used to weigh the DynVD at time t.
Overall, when the observed data show a linear dynamics, the next values expected from the IoT device can be approximated. Consequently, data sensing and transmission will follow a new time slot that depends on the observed linearity.
For the sake of clarity, we focus on a typical IoT application where a battery-powered device must periodically, every delta t time slot, carry out certain tasks and transmit the result to a sync node or a central controller node. This is the temporal requirement. The IoT application may expect an error threshold of epsilon that the values transmitted by the device should not exceed. The central controller node with high computation performance can control the device's activity, for instance, by imposing some particular settings. We model the transmitted values of the IoT device as a time series or a set of values x0 equals to x01, x02, x0n. With the conventional periodic sampling method, the data points are sensed and transmitted every delta t time slot.
In the IoT application, sensed values can be approximated or predicted. The prediction allows to avoid systematic data transmission, lighten the tasks of the IoT devices, save energy, prolong the lifetime of the application, and avoid multiple battery replacements. Gray model theory shows great performances in systems with uncertainty and poor or incomplete data. We adapt the gray theory model first order one variable prediction, GM11, in order to predict the future values that the IoT devices can sense.
Given a time series x0, a new sequence x1 is calculated with the accumulated generating operation AGO. The generated mean sequence Z1 is then derived from X1. The first-order differential equation of Gray model 1-1 is defined by the following equation. Thus, the Whitnian equation is the A and B parameters can be estimated with where the Y and B matrices are calculated like this. The x1 values at time k are consequently, next predicted values of the input data x0 at time k plus 1 is
Although the GM prediction smooths the randomness using the AGO function, it's important to remove outliers from initial data, especially with a small size of data and during the lifetime of the IoT application. To consider the limitation of IoT devices, we identify outliers using the Welford Online algorithm and the Chebyshev inequality.
we set the non-outliers range to x0 bar minus k times sigma to x0 bar plus k times sigma, with k equals to 5 and sigma is the standard deviation. To lighten the IoT calculations, sigma is incrementally computed, as we can read in the hard copy of our paper. xn bar is the mean of the sensed values. It is computed every time a value xn becomes available. xn minus 1 bar is the previous mean of the sensed values. According to the Chebyshev's inequality, if x is a random variable with a finite expected value mu and the variance sigma, then the probability that the difference between x and mu exceeds k times sigma is less than 1 divided by k squared. By setting k to 5, such probability is lower or equal to 0.04.
Our sampling and transfer strategy for IoT devices and a central controller node is duplicated using 3 new algorithms.
The IoT device should sense and return a value at most every delta t max time. This is the temporal requirement. Each returned value must not exceed the error threshold epsilon if compared to the raw value. This is the data accuracy requirement. W is the size of the prediction temporal window, which represents the input data used in the prediction and outliers removal. Algorithm 2 is performed continuously every delta t max by the central controller node. Algorithm 3 is carried out by the IoT device every time it wakes up before sleeping. When the sleeping time is up, the device performs the algorithm again and so on. In the first active cycle and before the first communication with the central controller node, the variables are not initialized. For instance, the sensing mode, prediction or send on delta, is not initialized. Line 12 in algorithm 3 guarantees a default send on delta mode. Similarly, line 4 guarantees a default epsilon before the first setting received from the central controller node. Line 5 transmits the first sensed value. Lines 2 in algorithm 3 and 3 in algorithm 2 are used by the central controller node to distinguish a flat battery from the absence of data due to the data transfer reduction. The message mentioned in line 17 in algorithm 3 is received from the central controller node in line 16 in algorithm 2 as an answer to the transmitted message in line 16 in algorithm 3. in Algorithm 3, the received delta Tmax is updated and used in the current active cycle. Lines 2 to 11 in Algorithm 1 allow the determination of which sensing mode should be applied by the IoT device and the controller node. The idea is, while the variation of raw data is within a tolerated error threshold of epsilon, it is better to keep the send on delta mode and avoid the prediction calculations and unnecessary transmissions from the IoT device to the central controller node. However, when there is a significant variation in raw data, the prediction becomes more interesting. Moreover, when there are many outliers, the last transmitted value, x last sent, can be affected and being itself outlier. Hence, send on delta becomes inefficient. Note that in this case, considering an older value, which means a value prior to the encountered outlier, as x last sent is risky for the required accuracy. With a high fluctuation of data during a temporal window W, the sampling and transfer is based on the prediction, while the new prediction is within the epsilon threshold. When the prediction deviates too far from real data during the window, the sampling mode becomes send on delta. This is an adaptive method to the fluctuation of raw data. It is a flexible way suitable for the tracked values dynamics. The moving window W includes the latest consecutive values with a size of W0, lines 17 to 24 in Algorithm 2. Sensed values with a variation higher than epsilon are sent with line 16 in Algorithm 3 to continuously follow the data evolution and adapt the sampling mode. The same sampling mode, SOD, send on delta or prediction, is applied by both the device and the central controller node. This is important because it ensures that the returned values by the central controller node are the same as the sensor node. As there is no systematic communication between the device and the central controller nodes, lines 19, 28, and 30 in Algorithm 3 ensure a persistent storage available in the next wake-up cycles of the IoT device. Lines 15 to 32 in Algorithm 3 ensure that the central controller node returns sensed values that entirely and strictly satisfy the requirements of errors with epsilon and temporal accuracy with delta Tmax.
For the performance evaluation, we use a data trace as a reference for the prediction. Data represent the sensed value outdoor temperature as transmitted by an IoT devices implemented using a Wi-Fi enabled ESP826612E board with a digital temperature sensor. A step-by-step implementation is available online on this link.
The reference data includes 7 months of measurements, near to 50,000 of samples with the 3 continuous periods P1, P2, and P3. Sampling or transfer rates are 1, 5, and 10 minutes.
We evaluate our prediction with and without outlier removal during the 3 periods P1, P2, and P3.
In this figure, the prediction is evaluated using the percentage error PE and the cumulative mean forecast error MAPE with and without outliers removal on data during the P1 period that includes near to 10,000 samples with a sample rate of 0.0167 Hz or each 1 minute. Here we can see the same prediction evaluation during the P2 and P3 periods, having a sample rate 5 and 10 minutes with a number of samples of 30,000 and 10,000 of samples respectively. We can observe that the predicted values are tracking favorably the trend of real data during P1 and P2 periods. This is confirmed by the low values of the mean forecast error MAPE metric and the mean absolute scaled error MASE metric, with a better performance when applying Outliers removal. For instance, in the P1 period, we get 5.98% of map with outlier removal against 6.28% without outliers removal. As expected, our predictions show better results regarding the accuracy with the FA indicator and the mean error with the MFE and the MAD metrics, and this is when the sample rate is low. Example, accuracy of 94.02% at a sample rate of 0.016 against 81.31% at a sample rate of 0.0033 Hz. The bad prediction accuracy observed in the P3 period can be explained by the strong variability of real values due to the low sampling rate. Another reason is the low values of the sensed data in this P3 period. Remember that the percentage error PE metric is a percentage related to the real values. This is confirmed by the high values of the MAD metric that accumulates the mean absolute value of the prediction error. Indeed, in the P3 period, the MAD metric is 2.48, while during a comparable period in terms of duration, for instance in the P1 period, the MAD metric is much smaller with a value of 1.44.
For a better match between the predicted and real values and to mitigate the effect of data variability, we consider a mover prediction windows W and evaluate the resulting performances. Only the last values sensed within the size of W are considered in the prediction.
Now we evaluate our predictions during the P3 period using the forecast accuracy metric FA and the mean absolute scaled error metric MASE with outliers removal and a moving prediction window. The size of the prediction window varies from 0 to 200 and then to 10,000. We observe a significant improvement of the prediction in terms of forecast accuracy and the mean absolute scaled error metric MASE during the P3 period when using a window size of 8. In period P3, the good match between predicted and real values is observed. A further performance improvement in all the periods P1, P2, and P3 is observed when compared to the prediction without the moving window. For instance, with a window size of 8, the accuracy in period P1 surges from 94.02% to 99.68%, and this is excellent.
In this part, we evaluate and compare the performance of our approach with the Bollinger Bands based approach DynVD, adapted to the limitations of IoT devices. To ensure a fair comparison, we evaluate DynVD within a large dataset during the periods from 1 to 3 by varying the parameters of the estimation function and identify the best setting of DynVD so that we can compare it with our approach.
As stated in the work of Culot et al., the variation of the buffer size n used in the DynVD approach has no significant impact on the error epsilon. Therefore, we set n to 8 to provide the best performance of DynVD. Moreover, this selected setting allows to use the same storage space of the IoT devices as in our approach. To be able to achieve a performance evaluation with a reference real-world dataset and evaluate the forecast accuracy of DynVD, the time slot delta t used in DynVD must be at least the value of the temporal threshold delta t max required by the IoT application. So, the IoT device can either sense or linearly approximate the data each required delta t max time slot. So, this implies the new condition. With a perfect linearity of the observed data, which means DynVD is equal to 0, the DynVD time slot delta t is the same as delta max. Conversely, when data are not linear, DynVD grows significantly and the DynVD time slot delta t approaches 0. In this case, DynVD cannot be evaluated with a reference data except if the DynVD time slot delta t is greater than or equal to the original time slot used in the reference data. During the 3 periods of our reference data, we measure the mean absolute deviation error MAD according to the value of delta max parameter. We also measure the number of samples transmissions required by the DynVD approach according to the value of delta max parameter. And here are the comparison results of the required transmissions with the DynVD approach with different delta max and our proposed approach according to the data accuracy requirement.
As we observed in the previous evaluation, the satisfaction of the accuracy requirement is evaluated according to the required epsilon and the number of the transmissions. That ensures the satisfactions of the epsilon by all the returned values. Our combination of the prediction and the SOD strategy avoids unnecessary calculations related to the prediction. The temporal requirement is satisfied by our algorithm's design. In the previous evaluation, the performance of our algorithm is compared with the best setting of DynVD. For each new period, we select a new sigma max that satisfies the epsilon requirement, which means the data accuracy, and with the smallest number of transmissions, which means the highest value of sigma max. Thanks to the performance evaluation, the selected sigma max enable DynVD to either sense or approximate data every sigma t max. While our proposed algorithms ensure that the error of returned values will never exceed epsilon, the MAD measurement of DynVD indicates that the overall mean error is less than epsilon. However, some values can violate the accuracy requirement. The performance result demonstrates the superiority of our approach. For the same requirement, our approach outperforms DynVD by requiring a smaller number of transmissions from the IoT device to the central controller node, whatever the required data accuracy. With the input requirements of accuracy and time slot, the same adaptive algorithm is applied for different periods, without a need to adjust the setting to face the fluctuation of tracked data. The important number of transmissions is observed during the period P2. This is explained by the fact that P2 is the longest period with an important number of samples. Although P1 and P3 periods have approximately the same number of samples, we observe that for the same value of epsilon, P3 requires more sampling than P1. This is due to the fluctuation of raw data in period P3 and its small sampling rate.
Here we show the transfer reduction gained by applying our proposed algorithm and by applying the DynVD approach during the periods P1, P2, and P3. The evaluation confirms the best performance of our algorithms in comparison to the DynVD strategy. While ensuring the desired precisions for all the returned values, the algorithms succeed to provide a high reduction of the number of transmissions if compared to the periodic sampling and transfer method. The proposed approach is very interesting in terms of bandwidth and energy saving for IoT sensor devices. For instance, with a guaranteed error threshold of 0.5, the algorithms save 84.29% of the IoT device transmissions. The performance becomes more beneficial for energy-efficient communications, particularly with unreliable networks links. In networks with a high network packet error rate, PER, saving only one transmission prevents additional retransmissions for all the related packets, application data, and network control. Thus, the consumption of energy is further reduced. We evaluate the energy saving of our proposed approach with a required data accuracy by the mean of an epsilon value of 0.5 and the following sample rates: 60 seconds for period 1, 300 seconds for period 2, and 600 seconds for period 3. The energy saving evaluation considers the same assumptions of the realistic energy comparison detailed in E. Moran et al. Without a network packet error rate, and based on the energy consumption model used in the work of X. Villajosana et al. As we can observe, it can be easily inferred that the percentage of energy saving is at least 84.25% of the energy required by the sensor to transfer data using the conventional periodic sampling. The good news is that in real-world usages, the expected amount of saved energy with our approach is much higher.
In this talk, I presented a new adaptive approach for reducing the sample transfer rate of IoT sensor nodes. We considered IoT applications with strict data accuracy and temporal requirements. We combined the gray theory prediction with outliers removal and a moving temporal window to guarantee data and temporal accuracy. The extensive experimental results demonstrated the effectiveness of our approach for IoT applications if compared to linear approximations adapted to the limitations of IoT devices. The results reveal that relying exclusively on prediction in sampling and transfer reduction for IoT sensor devices cannot guarantee the satisfaction of the strict application requirements, and this in terms of maximal error threshold and temporal accuracy. Without any assumption on the distribution of tracked data, we believe that the proposed combination of send-on delta strategy and the prediction will give for several real-world use cases the best results regarding the reduction of transfer rate, energy saving, and the strict satisfaction of accuracy requirements. The proposed approach is very beneficial for long-term IoT applications, particularly with IoT devices using energy-hungry transmission modules and require long periods of sensing and a high sampling rate. Thank you so much.